Okay, so we were in module 4. In module 4, we were talking about dynamic matrix control. Okay, so let's see where we are. One, with respect to state definition, step response model, and state space model. Okay, we have not talked about state space yet. We have primarily talked about step response models, but you will see that there are going to be parallels between state space and step response, which basically means that when operated upon by M, this guy gets discarded, this guy moves up, this guy moves up, and so on, so that you get y1k, y2k, and so on up to ypk. This is M y tilde k. Okay. Now let us talk about what was SUK and delta UMK. Just to remind ourselves, SU, not SUK, SU was equal to S1 S2 and so on up to SP, 0, S1, so on up to SP minus 1, 0, 0, SP minus M plus 1. Each of these elements S1 is Ny by Nu matrix. 0 is also Ny by Nu size 0 matrix. Okay. This is your SU, okay, and your delta U M K is delta U K, delta U K plus 1 and so on up to delta U K plus M minus 1. Okay. Delta U itself is Nu by 1 vector. Okay. So, this is basically what we have done so far. Okay. The next thing that we said is that we need to talk about, so second item was multi-step prediction. Third item is, let me call it third item A, objective function. Okay. And 10 days back we had talked about what objective function means and what type of objective functions are most common. Okay. So, the most common problems are going to be set point tracking problems, or disturbance rejection. Okay. In those cases, what we want to minimize is minimize a quadratic objective. Okay. So, minimize square of deviation from desired trajectory. Okay. So, let us take the case where the desired problem is that of set point tracking, okay, and the past we have somehow come to this particular location, okay, and let us say this is our predicted future. Okay. So, essentially what we are trying to say is that we are going to penalize this deviation from the set point. That is what we want to penalize, but how do we want to penalize? We want to penalize the square of that deviation. We usually, you would have studied integral of square of errors. Integral in discrete domain becomes sum. Okay. So, we want to minimize the sum of square errors, okay, and not just minimize it arbitrarily, but in a weighted manner. Let us look at this particular point. Okay. Let us say this is R, this value is Y. Okay. This is for variable 1, and let us say there are 2 variables and we want to minimize, let us say y1 minus r1 squared multiplied by some weight w1 plus we want to do w2 multiplied by y2 minus r2 squared. Okay. How this is represented, this particular guy, how this is represented is quite straightforward. This looks like a capital W. Right. R is a set point. We will come to that. For now, let us talk about in the plot that I have shown. Yes, R is constant. R is your set point. Okay, we'll just call it YSP. Yeah. Okay. You can verify that this works. This is nothing but inner product, right, multiplied by weight. This is absolutely nothing different, right, when, and you have done inner products before. Okay. So, at any time k, or let us say time k plus 1, okay, what is your weighted sum of square? Okay, it is nothing but this is what it is. Okay, to just link it with the previous slide. Okay, as I have said, we are going to deal with vectors only. So, let me not confuse you for posterity. R bar is just y bar sp. Okay. And again, I am not going to use bars. It is just, forgetting bars is actually going to be more confusing. So, I am not going to use under bars at all. Just assume, except for this particular case, everywhere else we are going to talk in terms of vectors only. Okay. And what is Q? Can I use a non-diagonal Q? Don't. Okay. There is nothing that stops you from doing it. Theories are all been developed for diagonal positive semi-definite Qs. Okay. But in practice, we have only tested it really very well for diagonal Qs with positive W values, or 0 or positive W values. So, you can use your W1 to be 0, you can use it positive, absolutely not negative. If you use a negative value of W, you cannot guarantee convexity of your optimization. Okay. And again, yeah, for people who work in this area would really understand the meaning of that statement. What that basically means is that you cannot guarantee that the curve is going to look something like this. The curve can look something like this, and if it does look something like this, or if it does have an inflection point, the final optimal result that you reach may not be the minimum. Okay. So, convexity is an extremely powerful concept when it comes to optimization. It guarantees that there is only going to be one minimum. Okay. So, yeah, do not use negative values of W. Okay. Even if, I mean, just do not do that. And again, do not use non-diagonal queues, just stick with diagonal queues. Okay. Okay. So, at time k plus 2, same thing is just going to be y k plus 2 at k minus r transpose q y k plus 2 minus r, and so on up to at time k plus p, it is going to be y okay. If we now want to put all of this in one big matrix, again the concept is quite simple, right. If you have an inner product of 1 2, inner product of 1 2 is nothing but 1 2 multiplied by 1 2, which is equal to 5. Okay. Let us say you want to do inner product of 1 2 and add that to inner product of 0 3. Okay. Inner product of 0 3 is nothing but 0 3 transpose multiplied by 0 3, which is equal to 9. Sum of these two is nothing but 14. Okay. Let us construct a bigger matrix, bigger vector, which is 1 2 0 3. What is the inner product of this? Inner product of this is 1 plus 4, which is 5, plus 9, which is 14, exactly same as the inner product of these. Okay. That is the reason why I spent almost 15 minutes talking about submatrices and matrix partitioning. Okay. This is just inverse of matrix partitioning. If you go from this and this to this, it is inverse of matrix partitioning. If you go from here to here, this is exactly what matrix partitioning is, right. And matrix partitioning, that concept works with inner product also. Okay. So, this was just an aside, just to give you an idea of what we are going to do. So, I guess by now you are probably guessed what is coming up, right. Sum of square errors, we wanted to add all of these. We wanted to add the error at k plus 1, error at k plus 2, error of k plus 3 up to error at k plus p. What does that do? Just construct this larger guy. Okay. So, how do you do that? Let us define something, I do not know what Z we will define, or we will define some Hindi language, K. We will define that as y k plus 1 at k minus r y k plus 2 at k minus r, and so on up to y okay, and let us define gamma y okay. I just showed you the inner product, weighted inner product just works in the same manner. Okay. If you think about partitioning, this is how the partitioning is happening, right. So, it just works in the same manner. Okay. So, what exactly is the sum of square errors? This is what the objective function with respect to sum of square errors or sum of square deviation from the set point is. Okay. Okay. If you just penalize the output the way I showed you on the previous page, your controller is going to be extremely aggressive. Okay. You do not want to do that, you want some kind of a regularization. Okay. And the way that is done is the overall objective I will just call that as okay. This is basically a regularization. Okay. What is delta um? Exactly what you had earlier. Okay. What is your gamma u? Okay. Keep in mind um is uk, uk plus 1 up to uk plus m minus 1, right. So, there are m nu by 1 elements in delta um. So, the gamma u matrix has to also reflect the same, which means R are repeated along the diagonal m number of times. The size of R is going to be equal to Nu by Nu. It is Nu by Nu diagonal matrix with the diagonal elements being the weights for U1, U2, U3 up to UNU. Okay. Okay. Next item is going to be constraints. Okay. Typical constraints are of the nature okay. So, let us recap the objective function. And constraints are this. We need to use this